In this video, I'm going to talk about the factors affecting resistance. It's part of topic 5.2 of the IB Physics Syllabus. It's relevant for both SL and HL students. Please take a moment to read the success criteria for this video. Okay, so when we do get a calculation and we get a value of resistance, we have three main categories that we put these materials into. Conductors, they have a very low resistance, and I'll talk mostly about what happens in conductors in this video. There's semiconductors, which are kind of in the middle. They also typically can change based on temperature or light, so like light-dependent resistors, things like that. You can see I have a video there. I think it's a really good one by MIT K-12. Please check it out if you want to know more about how the electrons behave in semiconductors. And finally, insulators. They're going to have a very high resistance. Okay, so let's talk about what's actually causing resistance. And as I said, here I'm going to be talking about mostly metals. So let's remind ourselves about what a metal looks like at a particle level. With the atom of a metal, what we have are the outside electrons are very loosely held, and so they're usually able to move freely throughout the metal. That's what these ones in red are. The inner electrons, though, and the nuclei are held and they stay put. So usually we say with a metal we have the sea of electrons and the fixed positive ions. Now, if I put the metal in an electric field, you can see I have all these electrons are moving this way. So I must have a positive on this side and a negative on this side. So that's what's actually going to cause my electrons to move through. But we still have these positive ions that are fixed in position, which means my electrons are going to have to move around them. That's what's going to cause my resistance. Now, I also, in this case, I have a pure metal. If there were impurities or this was an alloy, then obviously that would have more things in the way of these electrons, and that would increase the resistance. One last thing I want to point out is when we have current flowing through our metals, they also tend to get hot. So this resistance ends up causing a lot of collisions, as I just said. And what does that do? It transfers energy into thermal energy. So here I have a simple circuit. If I want to create an experiment in order to determine some of the factors of resistance, let's think about how we'd set this up. So first of all, I've got my resistor here. So if I want to perhaps measure the effect of the length of a wire, then I would take out this resistor and I would in its place put many different lengths one at a time and take my measurements. So let's think about what kind of measurements I'd have to take. If you remember from Ohm's law, we need voltage over current. So I need to set up a voltmeter. Remember, volts are potential difference. So that would be before and after the plate that I'm replacing. And then I also need an ammeter, and an ammeter would be put in series. So I could put one right there. So if I took my metal and I have 5 different lengths, if that's what I want to change, I would just replace it in that spot right there. And that means I could calculate from a graph my resistance. So here's a PhET simulation that you could go and measure and take a look at. It has the 3 main things that we will look at in terms of affecting resistance. One is resistivity. Now this is something that is inherent with the material. So if I have copper, all pieces of copper, assuming it's pure, will have the same resistivity. And that value will be different for zinc, which will be different for nickel. Okay, so resistivity is a property of the actual metal ion. Next is length. Notice where this is compared to my resistance. It's on the top, which means they're directly proportional. If I take a look at this little wire here, that should make sense because the longer I have as a piece of wire, that means the more atoms I'm actually having to move through. And finally, we have area, the cross-sectional area. So the area right here. Now, it's on the bottom, which means it's inversely proportional to the resistance. You might think at first, well, doesn't that make more electrons, and doesn't that make more nuclei have to get pi? Isn't that a problem? Think more in terms of a road. It's easier to get more cars down the road, i.e. electrons in your wire, if you have a multi-lane highway than if you have a single-lane highway. One last thing I want to point out is in the data booklet, this equation is actually written as resistivity equals resistance times cross-sectional area over length. It's exactly the same thing, but because I'm using in this video all about resistance, I've rearranged it. Okay, so let's check out a few questions just to make sure we can understand how to apply this understanding. We have a length of L, diameter D, resistivity of rho, and a resistance R. Now it says we have a second conductor, and instead of rho, it has 2 rho. It has a length of 2L and a 2D for diameter. Now, just a second here. Our equation doesn't have diameter. It actually has area. But if I want to think about that, area is pi r squared. And so if I put that in terms of diameter, that would be diameter divided by 2 in the square, or pi d squared over 4. Really important to realize. So it's a d squared. Now I'm going to cheat a little bit. Instead of just saying a here, I'm just going to write d squared because I know the pi over 4 is going to cancel out. So down here I need to put 2d and squared. If I clean that all up, I have 4 on the top, rho L d squared on the bottom, and I have 4 on the bottom, which means it's going to be exactly the same, and my answer is B. Okay, let's try another one. A 0.25 kilo ohm resistor is made of 50 turns of wire and wrapped around a non-conducting cylinder of diameter 8 millimeters. Determine the cross-sectional area of the wire. So let's think first about what it's given us. This 50 turns of wire around the cylinder. What is that trying to give us? Well, it's actually just trying to give us how to calculate the length. So the length of it is going to be going around the circumference. Let's figure out the circumference once. That would be 2 pi r, and it's done 50 times. So if I put my values in here, and then I'm going to get 1.26 meters. Now, I just want to point out here, don't forget that I have made the diameter into a radius, and I've also had to put it into meters. Next, let's take our equation and move it around to get area, and plug in our numbers. Again, notice that 0.25 is kilo ohms, so I have to put it into ohms. And when I put this into my calculator, I'm going to get 2.1 times 10 to the minus 9 meters squared. Okay, so here's an interesting problem I've found. Archaeologists using resistivity surveying of soil to research for the remains of buildings and settlements under the ground. So basically what happens when you have the soil that's been disturbed, we can actually get some changes in the actual resistivity. Now, in this case, you can see I've got the probes from 2 different places here, and they're measuring the current going through, and I put the potential difference here between B and C. So part A says, explain how the readings on the voltmeter will change if the length BC increases. Well, we just talked about how the length of a wire increases its resistance. So same here, the farther B and C are apart, the increase there will be in resistance. And what does that mean? It means that there'll be a greater potential difference from one end to the other if we have this constant current. One of the reasons I really like this question is because it's an application of your understanding. It's really important when you do the IB that you don't just assume that you're going to see the same questions over and over again. In fact, the top marks are going to go to people who can look at questions and they don't say, oh, I don't know how to do this one. They're going to look at it and say, what kind of understanding do I have that I can apply in this situation? Now we're going to get to one that even if you didn't get part A and you weren't sure of it, you should still be able to try and pick up some marks here. So I've got some values of resistivity. You can see how if it's disturbed or undisturbed or compacted, it's made a change in the resistivity here. So the probes are connected and kept at a constant separation of 0.75 meters and are moved along the soil between the different positions. We have a constant current of 9.5 milliamps, and we have a varying readings from 1.8 all the way up to 8.0. We can assume that the sample has a cross-sectional area of 0.65. So it says deduce two different possibilities, which means I need to be calculating some resistivity measurements and see how they relate to my table. Now, if I have my voltage being changed and a constant current, that tells me I'm going to have different resistances. So let's go and calculate those first. Okay, so I've substituted the numbers in and I get these two different resistances. But that's not what the question's asked. It's asked about comparing with the metals, and I need resistivity. So let's go back to the equation that we started with, and I'm going to move it around for resistivity. And I'm going to put these values in and see what I get. Okay, so here's the values I calculated. My minimum was 164. Now I've got lots of extra decimal places here, but it's just not needed. And my maximum will be 729. So what I need to do is I need to go back to my table and say, where do they fall into? 164, that is in this range right here. So I could say that we have some compacted clay. My other one, 729.8, that's going to be in the middle of limestone. So the two possible materials that I have present in here are compacted clay and limestone. Well, please take one more moment and go through the success criteria one more time. I hope after watching this video, you can actually say yes to all three of those points.